In this video, we're going to be discussing solids and how we go about determining the empirical formulas from unit cells. And so to start this off, we have two pictures on the page here, and the picture that's on the left has two crystals. It has a quartz crystal, and then you see there's little black crystals that look like diamonds. Those are anatase crystals. The image to the right is a crystal of rutile. Now, when we start talking about solids, these crystals have their own unique structures, their own sizes, and all this really depends on where they're formed at underground and the conditions. What's important here is that each of these crystals have their own empirical formula. So the quartz crystal that you see on the left hand side, so this is your quartz crystal, that has a formula of SiO2. And so in its unit cell, and a unit cell, we're going to talk about what that is in the future slide, but the formula is SiO2. It has an empirical formula of silicon and 2 oxygens. Now, the anatase crystal, which you can see here, there's multiple anatase crystals. All of those crystals have a formula of TiO2. Now we look at the right hand side, the rutile crystal that you see, the big crystal that you see, that has a formula of TiO2. Now these are all crystals, meaning that they have definite shape, size, and structure to them. And so solids can fall into two different groups. The first group being the crystalline group. Crystalline groups are going to have particles that are highly ordered in their arrangement. So when you look at a quartz crystal, it doesn't matter what quartz crystal you look at in the world, every quartz crystal has a hexagonal structure. And if you look at the picture here, you can see that each one of these structures has that six-sided shape to it. Always is going to adopt that hexagonal structure, and that's the crystalline structure that we see. Now, if you take the quartz crystal, and let's say over time it goes through the rock cycle and it breaks down and you walk across the sand at the beach, sand is actually silicon dioxide. And what they do is they take the sand from the beaches, and it's just an example. They take the sand from the beaches, they take it back to the plant that they're working at. Let's say you want to you break your windshield and you need a new windshield. What do? They take the sand, they melt it down, and they pour it into a form. And that the sand recrystallizes, but it doesn't necessarily recrystallize, it just resolidifies and forms what is called an amorphous solid. So when you look at all the windows, the glass that you have in your cars, your houses, wherever, all that glass is composed of silicon dioxide. The difference is that it's an amorphous solid, where if you look at a quartz crystal that has that definite shape and structure, that is a crystalline solid. So you have to be careful in understanding whether you're dealing with a crystalline solid or if you're dealing with an amorphous solid. An amorphous solid has no particular order to it or arrangement in the particles. It just forms so quickly to where the atom just kind of comes together and you get what you get out of it. For a quartz crystal, it takes thousands of years to grow, where glass takes merely just a few minutes to grow, or a couple hours at the most. So you have to understand the difference between crystalline and amorphous. So now, when we talk about the atoms and the way they align themselves, they arrange themselves in a specific way. Now remember that an atom is a spherical object. So it's a spherical circle object that when you put them close together, they're only going to arrange themselves in one configuration. Now if you look at the part that I'm circling here, they arrange themselves in that configuration. No matter what you do, you cannot rearrange those spheres just to pack any other way. And so that is the first layer that you find in a crystalline structure, is that layered pack of spheres. And we call that closed packed layer of spheres. Now, When you start to add on multiple atoms, they start to stack and build themselves into a three-dimensional object. There's two different ways that they can pack themselves. There is the hexagonal closed packed, and then there's the cubic closed packed. And if you look at the difference here, is that when you look at the hexagonal, it's going back and forth, and it's staircasing upwards. So you're going to have a straight linear line up the side of that crystal. However, if you look at the cubic closed, it's going A, B, C, and it's going to do the same configuration, but you can see it's not going to have that linear relationship to it. And so you get these different structures, and this is what really determines the crystal system that these different crystals fall in. So quartz crystals fall within that hexagonal structure. Now an example of a cubic closed pack would be calcite. And calcite forms a rhombohedral structure in its lattice. And so you can see that configuration there. However, a quartz crystal, it will always form the hexagonal structure that we saw in the first picture. So as these crystals grow, all right, their arrangements becomes more complex, and then what happens is as they get bigger and bigger, is they start to repeat themselves. And so when we start to see that repeating pattern, what we do is we pick out the beginning point to where it starts to repeat, and we call that the unit cell. And you can see that shaded in the blue here. This unit cell is the first thing that's formed, and then everything else is sort of forms around it, and that's how the crystal gets larger. Now, there's three different types of unit cells. There's primitive cubic, body-centered, and face-centered. If you look at the primitive cubic, you can see that the atoms are along the corners of that cube, and that's just representing the primitive cubic. If you look at the body center, well, you still see the atoms along the corners, but you also see the atom that's found in the middle of the unit cell, and that's why it's called body centered. Now, if you look at the other one, the last one is called face centered. Well, you still have your atoms along the corners, and that's going to be typically what happens, but what's different here, the atoms that are found along the face. And you can see there's 6 atoms because there's 6 different faces. So what we're going to do is we're going to take this unit cell and understanding the type of unit cell, and we're going to use that to our advantage in determining the empirical formula. So again, there are several types of basic arrangements in crystals like the ones we've saw and the previous, so primitive cubic, body centered, and face centered. Now, if you look at the way this drawing is drawn, you can see that not all of the spheres are found inside of the unit cell. If you look at the primitive cubic, only 1/8 of the atom is found inside of the unit cell. So the rest of that sphere is found in the other unit cells on the outside. If you look at the body center, you can see that still the corners are found to be 1/8 of an atom. But the one that's found in center is actually a whole atom. And then finally, the face center, you have half of the atom along the face. The other half is in the other unit cell to the side. So the position is important because we need to understand where the atom's found and ultimately what fraction of that atom is found in the unit cell. So I'm going to give you a second. Please go ahead and jot down the table that you see right here. You need that table and you need those values. If you're looking at your guide, you will find that table in the guide. So I'm going to come back in about 30 seconds. Okay, so hopefully you had enough time to jot that table down. So now we're going to look at a few examples. So we have 3 examples here. The first one is letter A. We have 2 different atoms in this unit cell. You have the chlorine, which is colored green, and you have the cesium, which is colored gray. And if you look at the unit cell, you have what type of unit cell? That would be a body-centered unit cell. And what that tells me is that the corners, since all the chlorines are found on the corner, there are 8 corners, so there's 8 chlorines, and each of those chlorines are worth the value of an eighth. So you do the math here, it's 8 times 1/8 is equal to 1. And so what we're trying to do is figure out the empirical formula based off the unit cell. The cesium, well, it's found in the center. There's only 1, and the value of the center is 1, and so that gives you 1 cesium. So putting these together, you have CsCl. So the empirical formula for this compound would be CsCl. Now I want you to think about going backwards and looking at the periodic table. What's the charge on cesium? What group is cesium found in? Cesium is found in group 1A, which has a +1 charge. And then chlorine is found in group 7A, which has a charge of -1. And so based off the charges, you should only have 1 cesium and 1 chlorine. And so our empirical formula does match up with what we learned in the first part of chemistry. So looking at the second one here, we have 2 different atoms again. We have sulfur and then we have zinc. So the sulfur, yellow colored, so we see that the sulfur is found on the corners, all right? But then if you look, it also is found on the face. You can see the face 1, 2, 3, 4, 5, 6. We found it on the face there. So for sulfur, you're going to have 8 times 1/8 because you have the corners, plus, because we have to add in the face now, there are 6 faces times 1/2. And so that equals what? 4. Now the zinc is gray shaded, and zinc looks like it might be on the face, but zinc is actually found inside. You can kind of see how the lines, you have to pay attention to lines point inward here, and this points inward. So all the zincs are found inside. There are 4 zincs. The value of that is going to be 4. So you have Zn4S4, but you know that in empirical formula is the simplest whole number ratio. So it's going to be Zns for that empirical formula. The last one, which possesses fluorine and calcium, if we look and we find the calcium, calcium is colored gray, and you see the calcium is found on the corners, 8 corners times 1/8, because there are 8 corners, plus, just like the previous one, you see that it is along the face as well. There's 6 of those times 1/2, and that gives you 4 for the calcium. Now the fluorine is blue. Where are the fluorines found at? They're found inside. And there's 8 of those. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 1. And that gives you a value of 8. So you have Ca4F8, which reduces to Ca F2. And if you go back and you look at your periodic table, you will find that that should be what the empirical formula is based off the charge of calcium, which is +2, and fluorine, which is -1. So as we see in this slide here, what we can get from the unit cells, we can determine based off of the arrangement of the atoms, we can understanding the type of unit cell we're working with, we can figure out the empirical formula for an ionic compound. And so that takes a little bit of practice. There is a worksheet that's found online, and there's several worksheets where you can go through and practice multiple unit cells. The hardest part is trying to determine the arrangement and where these atoms are found at, but always use the lines that you see drawn and how those lines are drawn towards the center or towards the outside, being able to determine whether the atoms are found on the face, the edge, or the center. We haven't even talked about a face in this example, but we did talk, I say a face, but an edge. We haven't talked about an edge, and an edge is actually found, you'll see that edges are found along the, well, edge of an atom. In fact, there are, 12 edges in a cube, so you would see your edges found here. Now remember, your edge is worth a quarter, and so you can figure out based off of the number of atoms that are found along the edges. So just keep that in mind. All right, we did do an example that uses an edge, but when you look at the worksheets, you're going to find examples that have edges in them. So be careful in trying to locate and just determine where those atoms are found in those cubes. So next thing we're going to do is we're going to talk about types of bonding in crystalline solids. And so on the left hand side, you'll see there are 4 types of solids. There's molecular, covalent, ionic, and metallic. We're going to start at the bottom with metallic, because metallic's the easiest one. If you find that an element is a metal, you're going to have a metallic bond or a metallic solid in this example. So all these examples that you see right here, all metallic elements, doesn't matter what metal you're looking at, they're found in the periodic table. And just a reminder here, you have your periodic table. If you find you have the staircase, if they're to the left of the staircase and they're not a metalloid, they're considered to be a metal. And so if you have just simple copper, well, that would be a metallic solid. Now, ionic is the next easiest one. Ionic solids are formed by metals bonding with nonmetals. A good example would be NaCl. NaCl, Na is a metal, Cl is a nonmetal, put together make an ionic solid. Now, the other two that we see here, covalent and molecular, these two are a little bit more of a challenge to determine, and it's all a matter of understanding the difference between molecular and covalent. And so what I like to think about whenever I'm looking at molecular and covalent, I like to think about hard versus soft. You say, if I hit you with a block of ice, it's going to hurt because it's hard. But if I let that block of ice sit there long enough, where's my evidence going to go? It's going to melt. Because water, even though it's hard, it's still a soft substance because it has a low melting point. And so what would we consider that? Well, water would be considered to be a molecular solid because it has a low melting point. So if you had dry ice, dry ice itself is just basically frozen CO2. It's just solidified. But if you leave a block of dry ice sitting on your table, what's going to happen to it? It's going to sublime. It's going to go away. And so CO2, even though, yes, block of dry ice is hard, it would hurt if you got hit by it. It's still a soft material, and so that would be considered a molecular solid. Now, if we take a quartz crystal or a glass, for example, if you take a piece of glass or quartz and you set it on your table, you come back, it'll be there when you're dying. That glass, that quartz crystal, will never go anywhere because it's has a very high melting point. It's very stable. And so quartz crystals are covalent. Covalent means it has a high boiling point. It's a hard substance. Diamonds. What do we do with diamonds? We use them to cut rocks. Diamond's the hardest substance on Earth. So diamond itself would be considered to be a covalent solid. Now, here's the trick though. When you look at diamond, all right, or carbon in general. So carbon can be in two different phases. It can be in a diamond phase. Yes, that's supposed to be diamond. And then it could be in a graphite phase. Which of those two are soft? Diamond or graphite? If you said graphite, then you're right. Graphite is a soft material. Graphite is actually going to be a molecular solid because it's soft. Every time you write with your pencil, you're writing with graphite. You're writing with carbon solid. Now, if you took a diamond and you were to write with it, you'd rip your paper in half because diamond is very hard, but graphite is very soft. So these are two good examples where graphite would be considered a molecular solid and diamond would be considered a covalent solid just because of the differences in their nature. And all that has to do with the way the atoms are arranged. Remember earlier we talked about crystalline versus amorphous. If you take a diamond out from underneath the Earth's crust and you bring it to the surface, what happens is that diamond over time will eventually convert into graphite because it doesn't have the pressure and temperature. That's something we talk about in phase diagrams in the previous slides of this chapter. So you got to be careful and trying to understand, okay, think about it. All right, is it going to melt easy? Is it going to go away very quickly? Or is it going to be something that sticks around for a long, long time? So being able to determine whether a solid is molecular or covalent, you got to think about it like that. But remember, there's four types of solids: molecular, covalent, ionic, and metallic. Using the information that we've learned here, and just thinking about it logically, how would you group it? So if I had a solid that was, let's say, KCl, what type of solid would that be? If you said ionic, you're correct. Because potassium is a metal and Cl is a nonmetal, and that falls within the ionic category. What if I had sulfur? What do you think sulfur would be? Sulfur is something that is relatively soft. It goes away very quickly. If you were to put a little heat to it, it would sublime very quickly. So that would be a good example of a molecular solid. So these are just different ways you think about the types of solids. Just start looking at different solids, thinking about, okay, how would we group this? Where would that fit in best? So looking at sodium chloride here, all right, this is a unit cell for sodium chloride. What we see here are the sodium atoms being the green one, the blue, teal, it's not green, but teal color. And then the chlorine will be the red one there. If we were to count around this, we would see, first of all, that it's a body-centered cell because you have that atom in the middle there. And yes, look where you find some of the other atoms. You find some of the atoms on the faces. And this is an example where you have atom along the edge. So going through and determining the empirical formula, what we would find here is we'd have one Cl and one Na. So the formula would be NaCl. Here's another example. This is galena, and this is an image that has multiple unit cells. If we were to figure out the empirical formula, what we would do is we would just take one of those unit cells and we would determine the empirical formula for that. Now, the Pb are the larger atoms, and what we see here are, in fact, let's see if we got that. have over here, I think. So we have 8 sides, and we have so there's nothing in the middle, there's nothing on the edge, and there's nothing on the face. So all of our atoms are found on the corners. And so looking at PB, there are 4 corners, and then each corner is worth an eighth. So that's going to give me 1/2 for my PB. Now looking at the sulfur, we can see that the other 4 corners are going to be representing the sulfur, and that's also going to be 8. So that's going to give you 1/2. So the formula would be PB 1/2, sulfur 1/2. But remember that it's going to be a whole number ratio. This is a fraction, but these 2 fractions are basically the same thing. So we can just round that up to PBS. So the empirical formula for galena would be PBS, and if you look right here, we get that formula for PBS. So that's how we determine the empirical formula for galena. Now the last slide here, we see 2 different examples of the diamond and the graphite. And what's important about the diamond is, in fact, you can't see it completely here, but a diamond actually has a structure that looks like this here, and it has 8 sides to it. Diamonds are octahedron, and they're octahedrons, meaning they have 8 sides. They're very ordered arrangements, and they're very tightly packed with the atoms, and that's why the diamonds are very hard substances. They cut through anything. However, graphite's different, because what happens when you take the pressure off of the structure of the diamond, the atoms still hold. Now if you look, you can kind of see that there's a hexagonal structure, and the carbon atoms still hold that hexagonal structure. You can see them here, and they stack themselves like that. And what they do is they align themselves in the different planes. Now they hold themselves together by intermolecular forces, and these intermolecular forces are fairly strong in a sense, but if you put a little bit of pressure, what happens when you write with a pencil is you take off a layer at a time, and every time you take a layer off, it gets smaller and smaller, as it should take. So that's why we say graphite is a soft material, and that's why graphite falls within the molecular solids, and diamond falls within the covalent solids. So I hope this video helps you understand what solids are, how we're able to use the unit cells to determine the empirical formulas, and then ultimately how to determine the type of solid that structure or crystal may possess. Thanks for watching.